Hey everybody, this is going to be a short video on how to do a type 2 average atomic mass problem. And when I say type 1, type 2, and type 3, that's my way of categorizing the problems. That's not something that you would find in a textbook. That's just me saying basically these problems come in three varieties, and I'm trying to help you know what to look for. So we said that when you do an average atomic mass problem, you list the isotopes using the hyphen notation. And this is, we started out putting the symbol and dash the isotope. So this problem is saying that gallium has two isotopes, gallium 71 with a specific mass of 70.92 AMUs and a percent abundance of 39.892%. And then it says, what's the mass of the other isotope? So I'm going to put a question mark there. We don't know the mass. We don't know anything about the second isotope. And so at first it looks like there's a lot of stuff missing here, because when we did the type 1 problems, we had, let me see if I can change the color here. Yeah, we had this whole column filled in, and we had the mass column filled in, and we had the percent abundances, and then we could change those to the decimal abundances. And then if you remember, we just multiplied. I told you to scratch out the percentage and then multiply the mass times the decimal abundance to get your subtotals, and then add the subtotals together. So the whole chart was filled in a type 1 problem. It was pretty easy. And you were solving for the final answer, which was the actual average atomic mass you would find on the periodic table. Well, this problem is a little different because it looks like we really don't have much information at all. So we know the mass of the first isotope, and we know its percent abundance, which we can convert into a decimal, 0.39892. Is there anything that you can think of that we can figure out about the second isotope to help us fill in this chart? Remember that if there are only two isotopes and one makes up about 40%, what does that tell you about the other isotope? It should make up about 60% of the total element found in nature. So if I take 100 minus 39.892, I get 60.108%. So remember, you should always be able to fill in that column if there are only two isotopes, because they have to add up to 100. Okay, so now that I know the percent abundance, I can change that to a decimal abundance, and I won't need this percent anymore. Okay, so that helped a little bit. We have some more information. Is there any way that we can figure out anything else on this chart? Anybody know where we could look to find the average atomic mass to help fill in that spot? We could look on the periodic table. So I need to go on my phone and look up average atomic mass, because I don't have a periodic table in front of me right now, of gallium. And it says it is 69.723. So for these type 2 problems, that's something that you're going to have to look up. The average atomic mass, unless it's given to you in the problem, and then you don't have to look it up because you already have it. Okay, so now we know everything except this value right here. So in the original problem, we would have taken, let me change to black so it shows up, 70.92 times its decimal abundance, which was 0.39892. We would have gotten our subtotal, and we would have added it to whatever the mass of the second isotope was, times its decimal abundance, which is 0.60108, and we would know that that would equal what's on the periodic table. So I hope that you can see what's different here. Before, we had everything we needed here, and we solved for the final answer. This time, the mass is missing. Instead, we know the final answer. So we're basically just going to put, you know, an M, or I would put an M for the mass that we're solving for right here. Put M. Okay, so how do I solve this algebraically? Well, I'm going to multiply 70.92 times 0.39892, and that gives me 28.291. Just keep a few decimal places there. And that plus 0.60108 M, I'm just rearranging these two M and the, just because I like to have the number first and then the letter, is equal to 69.723. So you have to combine like terms. This is a number and this is a number, so I can combine those together. If I subtract, stupid thing is in the way. If I subtract 28.291 from each side, I'll get rid of that. I'll just have 0.60108 M is equal to what's left on the other side, 69.723 minus 28.291. Oops, I entered it in my calculator wrong. 0.723 minus 28. Oh my gosh, you guys, I can't use this calculator. 69.723 minus 28.291. I'm sorry, that was painful. Is equal to 41.432. All right, now how do we solve for M? We have to divide by 0.60108 on both sides. And M is going to be equal to 68.929 AMUs. So that's the mass of the second isotope up here. That was our question mark. So that would mean this gallium here was probably gallium, what? 69, I would say, because it's 68.9. So that would round up to 69. Okay, so that's how you do it. You set up the expression where you have your missing mass. You put a variable in for, I put M in for it. And you look up the average atomic mass on the periodic table. And if you only have one percentage, you subtract from 100 to get the other one. You write your entire expression and solve for M. Okay, I could do another one. If I could figure out how to add, oh, there we go. Okay, so now I'm gonna do a second type 2 problem just so that you get a chance to see it again. This problem is dealing with boron, and it tells me in the problem that boron has two isotopes. The first one is boron 10, and I guess I'm changing the color accidentally with my wrist. Boron 10, which has a specific mass of 10.013 AMUs. And the percent abundance for that isotope is 19.9%. And so you can see that its decimal abundance would be, move the decimal 2 places to the left, 0.199. I can get rid of that, I don't need it anymore. And then it says boron has another isotope. Figure out what its mass is. That's all it tells you in the problem. Okay, so we have to take a little inventory and see what we can figure out. Remember, if there are only two isotopes present and they give you the percentage abundance of the one, you can easily figure out the percentage abundance of the other by subtracting from 100. So this would be 80.1%, which I can move the decimal 2 places to the left and convert immediately to a decimal. And I don't know the mass, so I'm actually going to replace that question mark with a variable, just an m for mass. And remember, you can look up the final answer on the periodic table, and for boron, it is 10.81 AMUs. So, okay, now I'm ready to set up this algebraic expression and solve for m. So if I take 10.013, the mass of the first isotope, times its decimal abundance, and add that to the mass of the second isotope times its decimal abundance, that should be equal to what's on the periodic table. So I have to multiply that first term, 10.013 times 0.199 is equal to 1.993. And then I'm going to rearrange this side just because it looks better like that. And then I'm going to set that equal to the other side. So I'm just saying I like to switch these two around because then the letter is at the end. Just makes more sense to me to solve for m at the end like that. Okay, so now when you solve an expression like this, you combine like terms. So I'm going to subtract the 1.993 over to the other side so that I combine the two number terms together. 10.81 minus 1.993 is equal to 8.817. So that's taken care of. And I have 0.801 m is equal to 8.817. So divide by the 0.801 on both sides, and you get m is equal to 11.007, and that unit would be AMUs. So that is the mass of our unknown boron isotope, 11.007. And I'll circle that in red just to make it stand out. And so the hyphen notation for that would be boron 11. Put AMUs as your unit for the mass. All right, so that's how you do a type 2 problem. You'll be missing one of the masses. You'll look up the final answer on the periodic table, and you'll write expressions and set them equal to that final answer. And if there are 3 isotopes, you just have 3 of these expressions, and there would only be one missing mass. If there were 4 isotopes, you'd have 4 of these expressions to work with and one missing mass. So that's a type 2. Now, please go try the type 2 problems on the PDF, and I think there are only 2, maybe 3 of them. There are a couple more mixed in on the next page that says homework, but I'm not asking you to do all that tonight, just the ones that are labeled type 2. Show your work, do it neatly on a clean piece of paper in your spiral notebook. Call it Average Atomic Mass Type 2 Problems. And good luck.